There are moments in the history of human knowledge when the universe itself seems to lean close and whisper something we were never meant to understand. These are rare, precious instants when our carefully constructed models of reality suddenly reveal themselves as partial glimpses of something far more vast, far more intricate, and infinitely more humbling than we had imagined. The launch of the James Webb Space Telescope in December 2021 was such a beginning. But the true moment of revelation, the instant when our cosmic perspective shifted beneath us like tectonic plates realigning, came in the summer of 2022, when the first images emerged from that remarkable instrument orbiting nearly 1 million miles from Earth. What we saw in those images was not merely surprising. It was, in a very real sense, impossible. And yet it was true. The James Webb Telescope turned its golden eye toward a patch of sky so small, so seemingly empty, that it occupied a space no larger than a grain of sand held at arm's length. This was not prime real estate in the cosmic landscape. This was a patch of darkness, a region that had been examined before by its predecessor, the Hubble Space Telescope, and found to contain a modest collection of galaxies, 3,000 or so, by the count of earlier surveys. When astronomers pointed JWST toward this same negligible corner of the universe, they expected confirmation. They expected validation. They expected to see what they had seen before. Instead, they saw 800,000 galaxies where 3,000 were thought to exist. The mathematics of this revelation is almost dizzying in its implications. If a patch of sky so small contains nearly 300 times more galaxies than previously believed, and we could theoretically replicate this observation across the entire celestial sphere, then the universe we inhabit is not the universe we thought we knew. The cosmos is not a vast expanse. It is incomprehensibly vaster still. What we had measured as a universe stretching 14 billion light-years across began to resolve itself as a universe spanning 93 billion light-years in diameter. In the time it takes to absorb that number, you are forced to recalibrate your sense of scale, your understanding of your place, and ultimately, your conception of what it means to exist at all. This is not merely a correction of a previous measurement, as if we had miscalculated the distance to a nearby star. This is a fundamental reappraisal of magnitude. It is as if a cartographer, having spent centuries mapping a kingdom, suddenly discovered that the kingdom is 6 times larger than every map suggested, and that the unexplored territories stretch beyond the farthest horizons, filled with cities and rivers and mountains that had remained hidden from human sight since the universe itself was young. But the revelations did not stop with mere quantity. As astronomers analyzed the light that JWST had gathered from these 800,000 galaxies, they encountered a problem that cut deeper, that challenged not just our measurements, but our understanding of how the universe itself works. These galaxies, many of them, had formed in an epoch when the universe was only 300 million years old. 300 million years. For perspective, consider that life on Earth has existed for nearly 4 billion years, and modern humans have walked this planet for merely 300,000 years. We are asking the universe to create, in a time period shorter than it has taken for the Andromeda Galaxy to complete a single orbit around the Milky Way, the structures we see in JWST's deep field observations. This is the problem. According to our models of cosmic evolution, this should not have been possible. The universe began in the Big Bang, approximately 13.8 billion years ago. In those first moments, there was only hydrogen and helium, primordial elements forged in the furnace of the expanding cosmos itself. Galaxies could not form instantaneously. They had to grow through the collision and merger of smaller structures, accumulating mass over time, drawing in gas clouds, igniting stars within their hearts. This process was thought to be gradual, a slow waltz of gravitation across billions of years. Yet JWST showed us massive galaxies, galaxies as large as our own Milky Way, already assembled when the universe was still in its infancy. The implications continue to proliferate like fractals spiraling infinitely inward. Black holes were discovered at the centers of these ancient galaxies, black holes of impossible mass. We have long understood that black holes grow by consuming matter, by drawing in stars and gas, and whatever comes too close to their event horizons. A black hole cannot be more massive than the galaxy around it, for it would have devoured all available fuel. Yet JWST revealed supermassive black holes that appeared to contain billions of solar masses when the universe was only 300 million years old. These black holes grew up too fast, accumulated mass too quickly, through mechanisms that our current theories cannot adequately explain. And then there are the structures themselves, vast filaments and walls of galaxies, stretching tens of millions of light years across, forming cosmic patterns of such complexity and magnitude that they should not have had time to assemble. Gravity works slowly, particularly on the largest scales. For a structure to grow to such immensity requires time measured in billions of years. Yet here were the cosmic structures, fully formed, when the universe was still finding its way, still cooling from its explosive birth. This is the moment we find ourselves in now, as we stand on the threshold of February 2026, nearly 4 years since those first images arrived from the observatory. The universe has revealed itself to be larger, more complex, and more puzzling than we believed. Every answer the James Webb Space Telescope has provided has spawned a dozen new questions, each one probing deeper into the mystery of how existence itself came to be. Part 2. The architecture of our understanding. To grasp the significance of what JWST has revealed, we must first understand what came before, not merely the previous observations of the cosmos, but the entire philosophical and scientific edifice upon which our understanding of the universe rests. This journey begins not with telescopes, but with the human impulse to wonder. For millennia, the universe was understood through the lens of philosophy and faith. The cosmos was thought to be finite, bounded, perhaps even geocentric, with Earth at its center and the heavens revolving around us in perfect, eternal circles. This was not a failing of ancient thinkers. It was a reasonable conclusion given the evidence available to their senses. The stars appeared fixed in their positions. The sun rose and set with predictable regularity. The universe seemed ordered, purposeful, perhaps even conscious of humanity's place within it. The telescopic revolution changed this picture. Galileo's simple instrument revealed that Jupiter had moons orbiting it, not Earth. The sun had spots. Distant stars did not blur into greater clarity, but remained points of light even under magnification, suggesting they were vastly farther away than anyone had supposed. Copernicus, before the age of telescopes, had already displaced Earth from the center, but it took the telescope to make his vision credible to the broad community of natural philosophers. Over the following centuries, the universe expanded in human imagination and knowledge. Newton's laws revealed that the same forces that govern motion on Earth govern the celestial spheres. The inverse square law, the law of universal gravitation, meant that the universe operated according to rational, mathematical principles. It was, in a sense, noble. Yet Newton's universe was also static, an infinite void filled with matter, a plenum in which light traveled in straight lines forever. The 19th century brought new revelations. Herschel, with his reflecting telescopes, began to map the distribution of stars, to wonder whether the sun was central to a vast disk of stars, which we now call the Milky Way. The 19th century also brought thermodynamics, the recognition that energy flows from hot to cold, that the universe was winding down, that entropy always increased. This was a universe with a history, a beginning perhaps, and certainly an ending. The universe was no longer static. It was dynamic, evolving, changing. The 20th century witnessed the first true cosmological revolution. Einstein's theory of general relativity, published in 1915, revealed that space and time were not separate, absolute entities, but were woven together into the fabric of space-time itself, a fabric that could be curved by the presence of matter and energy. This curved space-time told matter how to move, and matter told space-time how to curve. It was a profound inversion of Newtonian thinking, and it immediately opened new possibilities for understanding the universe as a whole. In 1929, Edwin Hubble made his discovery that would reshape cosmology forever. By measuring the distances to galaxies beyond our own and observing their light, he found that the universe was expanding. The farther away a galaxy was, the faster it was receding from us. This was not a Doppler shift of a static universe, as some had previously thought. It was evidence that space itself was expanding, stretching, growing. Hubble's observation was revolutionary in its implications, yet it was also sobering in its simplicity. If the universe is expanding now, then in the past it must have been smaller, denser, hotter. Extrapolate back far enough, and you arrive at a moment of infinite density and infinite temperature, a singularity, a beginning. This was the genesis of the Big Bang Theory, though the term itself was coined somewhat dismissively by Fred Hoyle, who favored the rival steady-state hypothesis. The Big Bang, as developed by Lemaitre and later by Gamow and others, proposed that the universe began in an extraordinarily hot, dense state and has been expanding and cooling ever since. The early universe would have been dominated by radiation, by pure energy. As it expanded and cooled, the fundamental forces that were unified in the earliest moments would have separated, strong and weak nuclear forces parting ways, the electromagnetic force distinguishing itself from the weak force. In that early universe, there would have been no atoms, no stars, no galaxies. There was only a roiling sea of subatomic particles and radiation. Yet as the universe continued to expand and cool, protons and neutrons would have combined to form the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. This moment, occurring roughly 3 minutes after the Big Bang, is called Big Bang nucleosynthesis. The predictions of this process matched observations of the abundances of these light elements in the universe today. This agreement between theory and observation was profound evidence that the Big Bang model was essentially correct. But for the first 380,000 years after the Big Bang, the universe remained opaque. Radiation dominated the cosmos, and the photons of light could not travel far before being absorbed and re-emitted by the dense plasma of electrons and nuclei. It was a universe shrouded in fog. Then came the moment of recombination. As the universe cooled to about 3,000 Kelvin, electrons combined with nuclei to form neutral atoms. Suddenly, the photons could travel freely through space. Light decoupled from matter. The universe became transparent. This moment left an imprint on the cosmos, a faint afterglow of the Big Bang itself, a cosmic microwave background radiation that filled all of space uniformly. This radiation was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were puzzled by a persistent noise in their radio antenna at Bell Labs. That noise was the whisper of the early universe itself, a cosmic echo of the Big Bang. The subsequent measurement of the cosmic microwave background, particularly the precise measurements from the WMAP and Planck satellites, showed that the universe was extraordinarily uniform on large scales, with only tiny variations in temperature, fluctuations of 1 part in 100,000. These tiny fluctuations were crucial. In a perfectly uniform universe, gravity would have no handle by which to begin building structures. Overdense regions would need to begin somewhere. These fluctuations in the cosmic microwave background represented exactly such seeds. Regions that were slightly denser than average would attract more matter through gravity, growing denser still. Over billions of years, these seed fluctuations would grow into the cosmic web, a vast network of filaments and walls concentrated around dark matter, populated with the galaxies that we see today. This, then, is the standard model of cosmology, the framework within which astronomers had, until recently, understood the evolution of the universe. The universe began 13.8 billion years ago in the Big Bang. For the first 380,000 years, it was opaque and formless. Then came the moment of recombination, and the universe became transparent. For the next 100 million years or so, the universe remained dark, what we call the cosmic dark ages. Stars had not yet formed. Galaxies had not yet assembled. There was only the original hydrogen and helium, drawn together by gravity, beginning to collapse into the first stars. These first stars were different from the stars we see today. They were composed only of hydrogen and helium, with no heavier elements. They were massive, burning their fuel quickly, living and dying in a cosmic eye blink. As they died, they forged heavier elements in their cores: carbon, oxygen, silicon, iron. When they exploded as supernovae, they scattered these elements across space. Subsequent generations of stars incorporated these elements, allowing for the formation of planets and, eventually, life. Galaxies assembled from clouds of dark matter and the ordinary matter that collected within them. These galaxies began as small structures and grew through mergers, consuming one another, building into the massive galaxies we see today. Our own Milky Way is thought to be the product of several such mergers, the last major one occurring a few billion years ago when it collided with a large galaxy called the Sagittarius Dwarf Elliptical Galaxy. This process of galaxy formation and growth was thought to be gradual, occurring over billions of years. The light from the most distant galaxies, which we observe as they were in the ancient universe, showed relatively modest structures. The galaxies appeared smaller, less developed, more chaotic than nearby galaxies. There seemed to be an evolution, a progression from simple beginnings to greater complexity over cosmic time. This was the picture that had been carefully assembled over decades of observation and refinement. And then the James Webb Space Telescope looked into that patch of empty sky and saw 800,000 galaxies, and everything seemed to shift beneath us. Part 3. The Abyss Gazes also. The discovery of 800,000 galaxies in what was thought to be a relatively empty patch of sky is difficult to visualize because it exists at a scale that human experience has not prepared us to comprehend. We are creatures of a particular size, living on a particular planet, moving at particular speeds. Our intuitions about quantity, distance, and scale have evolved to serve us in a world measured in meters, seconds, and kilograms. The universe operates at scales that are utterly alien to this experience. Consider the observable universe. The term, observable, is crucial. It does not mean the entire universe. It means the portion of the universe from which light has had time to reach us since the beginning. The radius of the observable universe is approximately 46.5 billion light-years. A light-year is the distance that light travels in 1 year, moving at 300,000 kilometers per second. Multiply that distance by 1 year, and you get a number so vast that it defies intuition, approximately 9.4 trillion kilometers per light-year. Now, the observable universe has a radius of 46.5 billion light-years. This means its diameter is approximately 93 billion light-years. The volume of a sphere with such a radius is roughly 4 times 10 to the 35th cubic light-years. Within this cosmic volume, we now believe there are approximately 2 trillion galaxies. 2 trillion. That is 2,000 billion. That is the numeral 2 followed by 12 zeros. To write out 1 trillion seconds in words would take more paper than exists on Earth. If you counted to 1 trillion at a rate of 1 number per second, it would take 31,000 years of continuous counting. The Hubble Space Telescope, launched in 1990, has been instrumental in refining our understanding of the number of galaxies in the universe. In 1995, astronomers pointed Hubble toward a small patch of sky in the constellation Ursa Major, a region covering only about 1% of the full moon's diameter. This was the Hubble Deep Field. For 10 consecutive days, Hubble stared at this region, collecting photons, building up an image of what lay in that seemingly empty darkness. When the image was revealed, it showed 3,000 galaxies in that small patch. The implications were staggering. If this small patch was representative of the universe as a whole, and you could tile the entire sky with such patches, you could calculate the total number of galaxies in the observable universe. The result was somewhere around 50 billion to 200 billion galaxies, with estimates varying depending on assumptions about how the density of galaxies varied with distance. As telescopes improved, and as astronomers took deeper and deeper observations, pushing toward greater distances, and therefore looking back toward earlier times in the universe's history, the estimates began to shift. A 2016 study by Christopher Consolis and colleagues suggested that the number might be as high as 2 trillion galaxies, based on analyses of deep field observations and careful statistical modeling. The James Webb Space Telescope, with its larger mirrors and its infrared sensitivity, has been able to peer even deeper into space and earlier into time. Its deep field observations, released in the summer of 2022, seem to confirm and strengthen these higher estimates. The sensitivity of JWST is such that it can detect galaxies that were invisible to Hubble. These are often very distant galaxies, appearing as they were when the universe was very young, and they are often very faint, their light redshifted into the infrared by the expansion of the universe. What JWST revealed is that there are even more of these faint, distant galaxies than had been anticipated. The universe is not just larger in the sense of containing more galaxies, it is denser in galaxies at greater distances, and it contains a higher fraction of small, faint galaxies than previous models had suggested. This means that the universe is, in a very real sense, busier than we had thought. There is more structure, more complexity, more galaxies scattered through the cosmic void. To understand what 800,000 galaxies in a single deep field means, we must first grasp the nature of these observations. The human eye has a limit to its angular resolution, roughly 1 arc-minute in good conditions. An arc-minute is 1/60th of 1 degree. To appreciate the scale, hold your arm outstretched and raise your hand flat with fingers together. Your hand at arm's length covers about 10 degrees of sky. Now imagine dividing that into 100 equal parts along one side. Each part is 1/10 of a degree, or 6 arc-minutes. Divide further, and 1 arc-minute is a very small patch of sky. The Hubble Deep Field image covered about 134 square arc-minutes. The JWST Deep Field image covers a similar area. In this small region of the sky, no brighter than a grain of sand at arm's length, there are 800,000 galaxies. Each of these galaxies is typically composed of billions of stars, bound together by gravity into a coherent structure. Each galaxy contains worlds, potentially many of them, arranged in orbits around those stars. the implications for the total number of galaxies in the observable universe are profound. If we scale up from that small patch to the entire sky, covering all 41,132 square degrees of the celestial sphere, we arrive at a figure that has been estimated to be as high as 20 trillion galaxies, though estimates vary depending on assumptions about galaxy counts at very great distances. 20 trillion galaxies. This is a number so large that it becomes almost meaningless, stripping away coherent meaning in the way that very large numbers always do. The human mind evolved in an environment where we encountered at most dozens of objects at a time. We can intuitively grasp the difference between 5 and 10, between 100 and 200. But the difference between 1 trillion and 20 trillion is incomprehensible in the way that the difference between a pebble and a mountain is not. There is no evolved intuition for these numbers. Yet this inflation of our cosmic senses is not the most profound part of what JWST has revealed. The truly unsettling discovery is not the number of galaxies, but their age, or rather, the age of the universe when these galaxies formed. To understand this, we must consider the relationship between distance, time, and the expansion of the universe. When astronomers observe distant galaxies, they are looking backward in time. Light travels at a finite speed. The farther away an object is, the longer its light takes to reach us. Therefore, the light from a distant galaxy, if it is billions of light years away, left the galaxy billions of years ago. Observing the most distant galaxies is equivalent to observing the universe as it was in its youth. The relationship between distance and time is mediated by the expansion of the universe. This expansion means that the universe is not like a cloud of galaxies scattered through infinite static space, with light traveling to us in straight lines through the void. Instead, the space itself is expanding, carrying galaxies apart, and light traveling through expanding space is redshifted, its wavelength stretched, its frequency lowered. This redshift is characterized by a quantity called the redshift parameter, often denoted z. A redshift of z equals 1 means that the wavelength of light has been doubled by the expansion of the universe. For higher redshifts, the relationship becomes more complex, dependent on the properties of the expanding universe, but the principle remains. Higher redshift means greater distance and earlier time. The first galaxies are thought to have begun forming around 200 to 300 million years after the Big Bang. These would be the earliest objects visible to JWST, appearing at redshifts so high that they are difficult to observe even for this remarkable instrument. But the question is how fully formed these early galaxies were, how massive, and how quickly they assembled. The earlier models of galaxy formation suggested a hierarchical process. Small structures formed first, then merged to form larger structures, which merged to form even larger structures, in a cascade of assembly that took billions of years to produce the giant galaxies we see today. In this picture, the very first galaxies would be small, faint, and relatively numerous. As time progressed, galaxies would grow larger and fewer through mergers. The ratio of massive to faint galaxies would increase with time, as the population of small galaxies was consumed by larger ones. JWST observations seem to show something different. The early universe appears to contain more massive galaxies than these hierarchical models predicted. Moreover, the massive black holes that live in the centers of these early galaxies appear to be too large, overweight, so to speak, relative to the galaxies that contain them. In the nearby universe, there is a tight relationship between the mass of the central black hole and the mass of the galaxy's bulge. Black holes with masses of millions or billions of solar masses reside in the centers of galaxies, with correspondingly massive central regions. But in the early universe, JWST is finding black holes that are too massive for their host galaxies. This is puzzling because black holes grow by consuming matter. If a black hole is more massive than the galaxy's central bulge, it seems that the black hole would have to have accreted all the available material. In the early universe, there was less time for such accretion. Mergers were supposed to be rare in the early universe because structures were still assembling, still spread out across great distances. Yet somehow, black holes achieved great masses in a short time. The mystery deepens when we consider the structures on even larger scales. The cosmic web, the vast filaments and walls of galaxies that permeate the universe, appears to be assembled at scales that are too large given the young age of the universe. The structures we see in redshift surveys of galaxies, maps showing which galaxies are where, and how fast they are receding from us, reveal patterns of staggering size. The Hercules Corona Borealis Great Wall is a filamentary structure stretching more than 1 billion light-years across. The Sloan Great Wall, another cosmic structure, spans over 1.4 billion light-years. These are not mere coincidences of alignment, like stars that appear close in the sky but are actually far apart in three-dimensional space. They are gravitationally bound structures, coherent assemblages of matter held together by gravity. For such structures to form requires time. Gravity acts slowly on the largest scales. The growth of cosmic structures is a process that proceeds through the ages of the universe, as the slight overdensities present in the early universe grow through gravitational instability into the grand structures we observe today. Yet in the early universe observed by JWST, these structures appear to be assembled more rapidly than the theory predicts. It is as if the cosmic architecture is being built on an accelerated schedule, as if the contractors had somehow found a shortcut through the laws of physics. Part 4. The Paradox of Scale. The situation we find ourselves in is that of a profound paradox. On one hand, we have observations, direct light from distant galaxies, collected by the James Webb Space Telescope, analyzed with precision, and published in peer-reviewed journals. These observations show clearly that the early universe contained more and more massive structures than predicted by our current models of cosmic evolution. On the other hand, we have theoretical frameworks, models of how the universe expands, how gravity draws matter together, how structures form and grow, that have been tested countless times and have proven remarkably accurate in making predictions about the universe we observe today. This is the creative tension at the heart of modern cosmology. It is not a crisis that suggests the entire framework of Big Bang cosmology is wrong. The cosmic microwave background radiation, the abundances of light elements, the expansion of the universe, the properties of distant supernovae, all of these confirm that the basic model of the Big Bang is sound. Rather, it is a challenge to the details of how structures form within that expanding universe, and what role dark matter, dark energy, and the initial conditions of the universe played in determining the universe we see today. To grasp the nature of this challenge, we must consider what it takes for structure to form in the expanding universe. In the beginning, the universe was smooth, almost perfectly uniform. The cosmic microwave background radiation shows us a universe that is the same to 1 part in 100,000 in temperature in all directions. This uniformity is striking. If the early universe were perfectly uniform, perfectly smooth, it would remain so forever. Gravity would have no leverage by which to act. All the matter would continue to expand outward uniformly, like a rising bread dough, with no clumping, no structure, no assembly into galaxies and stars. But the universe was not perfectly uniform. The cosmic microwave background radiation also shows tiny temperature fluctuations, regions that are slightly hotter and slightly colder than average. These fluctuations correspond to regions where the matter was slightly denser and slightly less dense than average. Regions of slightly greater density would attract more matter through gravity, growing denser still. Over billions of years, these seed fluctuations would grow through the process of gravitational amplification into the structures we see today. The initial fluctuations, we believe, were quantum in nature. They arose from quantum uncertainties in the very early universe. Some of the most successful models of the early universe, inflationary models, predict specific properties for these fluctuations. They should be Gaussian in distribution, meaning they follow the standard bell curve, with very large and very small fluctuations being rare and small fluctuations being common. They should also be essentially scale invariant, meaning that the amount of fluctuation at a given scale is roughly independent of the size of that scale. These predictions have been tested against observations of the cosmic microwave background and of the distribution of galaxies in the universe, and they have been confirmed to remarkable precision. Yet there is a constraint. The larger a structure is, the more slowly it can grow through gravity. A galaxy can grow on timescales of billions of years through the merger of smaller structures. But a structure spanning tens of millions of light years, a feature of the cosmic web, needs to be nearly in place from the beginning, imprinted into the initial conditions by inflation or some other process in the early universe. The problem is that if you scale up the initial density fluctuations that are observed in the cosmic microwave background to larger scales, using the predictions of inflation, you do not find enough large-scale fluctuation to explain the structures observed in the early universe by JWST. There is a shortfall. The universe appears to have assembled its large-scale structure more efficiently, more rapidly, or with more initial fluctuation on large scales than the standard models predict. There are several possible resolutions to this problem. The first is that our understanding of dark matter is incomplete. Dark matter is thought to comprise about 85% of all the matter in the universe, far outweighing ordinary matter. We have never directly detected dark matter. We know it exists only through its gravitational effects. Perhaps dark matter behaves differently than we think. Perhaps it clusters more efficiently than our models suggest, or it has properties that allow structures to form more rapidly. The second possibility is that the early universe was different than we think. Perhaps inflation, the theory that explains the uniformity and structure of the universe, was not the only process at work. Perhaps there were other processes that seeded additional structure that created fluctuations on larger scales than inflation typically produces. Or perhaps inflation itself was more exotic than we imagine, with properties that led to a distribution of matter different from what standard inflation predicts. A third possibility is that the universe contains more ordinary matter than we think, and less dark matter. This would allow for more rapid structure formation, because gravity would have more matter to work with. However, this runs counter to other observations, particularly of the cosmic microwave background, which constrains the total amount of ordinary matter in the universe quite precisely. A fourth possibility is that our understanding of gravity itself is incomplete. Perhaps on the largest scales, gravity behaves differently than general relativity predicts. There have been various proposed modifications to gravity, theories that add extra dimensions, or extra fields, or change how gravity operates at large scales. Most of these modifications have been ruled out by observations, but perhaps one of them, or an entirely new idea, is on the right track. A fifth possibility is that the observations themselves are misleading. Perhaps the galaxies that JWST is observing in the early universe are not quite what we think they are. Perhaps some of them are blended, multiple fainter galaxies appearing as a single brighter galaxy due to the limitations of the telescope's resolution. Perhaps the distances to some of them are measured incorrectly. Perhaps some of the light is lensed by massive structures between us and the distant galaxies, magnifying them and making them appear more massive than they truly are. This last possibility is particularly intriguing because gravitational lensing is a well-understood phenomenon, a direct consequence of general relativity. When light from a distant object passes near a massive structure, a galaxy, a cluster of galaxies, or a dark matter concentration, the spacetime is curved and the light path is bent. If the geometry is right, multiple light paths can arrive at Earth from the same distant source, creating a magnified or multiple image. Gravitational lensing is so common that astronomers must account for it when interpreting observations of the distant universe. Could gravitational lensing explain away some of the JWST observations? Perhaps some of the galaxies that appear to be at very high redshifts are actually foreground galaxies, magnified by lensing. But the JWST team has been careful to account for this possibility, examining the spectroscopic properties of the galaxies they observe to distinguish between true high redshift objects and lens objects. While some lensing does occur, it does not appear to account for the full discrepancy between observations and predictions. What we are left with, then, is a genuine puzzle. The universe appears to have created structures, galaxies, black holes, cosmic walls and filaments more rapidly, more efficiently, or in greater abundance than our current models predict. This is not a small discrepancy that can be resolved with minor tweaks to the models. It is a fundamental challenge to our understanding of how the universe evolved from a smooth, nearly featureless beginning to the structured cosmos we see today. In a very real sense, JWST has unveiled not a solution to the mystery of cosmic origins, but a new puzzle, one that may require deeper insight into the nature of gravity, dark matter, inflation, or some other aspect of fundamental physics that we have not yet fully grasped. Part 5. The Age of Impossibilities. Consider the problem from a slightly different angle. When we observe a galaxy at very high redshift, say Z equals 10, which corresponds to an epoch when the universe was only about 500 million years old, we are looking at an object that appears to be quite massive. The number of stars it contains, inferred from its luminosity, suggests a total stellar mass in the billions of solar masses. This is a significant galaxy, comparable in heft to a large elliptical galaxy in the nearby universe. Now, how did this galaxy assemble itself in the time available? The conventional picture of galaxy formation, the hierarchical assembly model, says that galaxies grow through mergers. Small galaxies coalesce into larger galaxies, which then merge into even larger galaxies. But mergers are not instantaneous events. When two galaxies collide, it can take hundreds of millions of years for the process to complete. The stars themselves almost never collide. They are too small compared to the distances between them. But the gas clouds collide, merge, and heat up. The gravitational dynamics of the two systems slowly reach an equilibrium, and the result is a single, larger galaxy. Moreover, mergers were thought to be relatively rare in the early universe. The density of galaxies was lower then. They were more spread out, farther apart. For a galaxy to find another galaxy to merge with, it had to exist in a region where galaxy density was higher than average. In the hierarchical model, such regions were rare in the very early universe. Small clumps of galaxies could exist, but most of the space was relatively empty. Furthermore, in the early universe, there was relatively little time for a single galaxy to grow through the accretion of gas and the formation of new stars. A galaxy grows by two main mechanisms: mergers with other galaxies, and the accretion and consumption of gas from the intergalactic medium. The gas in the intergalactic medium is diffuse, spread thinly across space. For a galaxy to grow significantly through accretion alone would require a long time, on the order of billions of years. Yet JWST is observing massive galaxies at redshifts of z equals 10 or even higher. These galaxies appear to have assembled themselves in a few 100 million years. How? One possibility is that the very first galaxies formed more efficiently than we thought. Perhaps the process of converting gas into stars was more rapid, more complete, more effective in the early universe than in nearby galaxies today. In the nearby universe, galaxies typically convert only a small fraction of their gas into stars. Most of the gas is eventually blown out by the energy released by supernovae or by accreting supermassive black holes. But perhaps in the early universe, this feedback mechanism was weaker, or galaxies were better able to retain their gas, allowing them to convert a larger fraction into stars. Another possibility is that the very first galaxies were different in character from what we observed nearby. Perhaps they were extremely compact, with stars packed in more densely than in modern galaxies. Perhaps they were rotationally supported and rotating rapidly, unlike the more chaotic merging galaxies we might expect in a hierarchical universe. Indeed, JWST observations do suggest that some early galaxies are surprisingly rotationally supported and disk-like, more structured than the tumbling, merging galaxies that populate simulations of hierarchical galaxy formation. A third possibility is that the universe contained initial density fluctuations on large scales that were larger than inflation predicts. If some regions of the early universe were denser than others by an amount greater than inflationary theory allows, then galaxies in those dense regions would form earlier and more copiously. The universe, in this scenario, would have been lumpier from the beginning than standard inflation suggests. The presence of massive black holes in the early universe compounds the mystery. Supermassive black holes, with masses of millions or billions of solar masses, reside in the centers of most nearby galaxies. They play an important role in the evolution of galaxies, regulating the rate at which gas can be converted into stars through the release of jets and radiation. But how did these black holes grow to such massive sizes in the early universe? Black holes grow by consuming matter. A black hole that initially forms from the collapse of a massive star might have a mass of 10 to a few tens of solar masses. For it to grow to a mass of 1 billion solar masses requires a long process of accretion. If the black hole is always limited by the supply of gas nearby, if it can only consume gas at a certain rate, then growing from a few tens of solar masses to 1 billion solar masses would require a very long time. The timescale for black hole growth is constrained by the Eddington limit, a theoretical limit on the rate at which a black hole can accrete mass. At the Eddington limit, the radiation pressure from the light emitted by the infalling gas exactly balances gravity, preventing further accretion. If a black hole tries to accrete faster than the Eddington limit allows, it will blow away the surrounding gas with radiation pressure. Therefore, black hole growth is limited by the Eddington limit, and there is a maximum rate at which a black hole can grow. If a black hole of 10 solar masses were to grow at the Eddington limit, starting from when the universe was 100 million years old, it would take approximately 1 billion years to reach a mass of 1 billion solar masses. But the universe was only 300 million years old when JWST observes the earliest black holes. This is not enough time for a black hole to grow from stellar mass to supermassive mass at the Eddington limit. Could black holes have grown faster than the Eddington limit? Perhaps if the supply of gas was extraordinarily abundant, the accretion rate was somehow able to exceed the Eddington limit. Or perhaps the initial seed black holes were not small. Maybe they formed directly as black holes of thousands or millions of solar masses, rather than growing from the collapse of stars. The latter possibility is interesting. Standard theory predicts that black holes form when massive stars reach the end of their lives and collapse. The smallest black holes that form this way have masses of a few solar masses. But there are alternative paths to black hole formation that have been explored in recent years. Perhaps in the very dense cores of the earliest star clusters, many stellar mass black holes could merge to form a more massive black hole. Or perhaps supermassive black holes could form directly from the collapse of clouds of gas in the early universe, without going through a stellar phase first. This process, called direct collapse, would require the right conditions: extremely dense clouds that had not yet fragmented into stars, but such conditions might have existed in the very early universe. If supermassive black holes could form directly from gas collapse, they could begin their lives at masses much higher than stellar collapse would allow. A black hole formed directly from a gas cloud could potentially begin at a mass of thousands or millions of solar masses, or even higher. From that starting point, even modest growth through accretion over several 100 million years could result in the billion solar mass black holes that JWST observes. This is speculation, educated speculation based on theoretical models, but speculation nonetheless. The honest truth is that we do not yet know how the early universe generated supermassive black holes so rapidly. It is one of the enduring mysteries that JWST has brought into sharp focus. Part 6. The Cosmic Web in its Youth. If we pull back further still, zooming out from individual galaxies and their central black holes to consider the structure of the universe on ever larger scales, the puzzles only deepen. The universe is not uniformly populated with galaxies. Instead, galaxies are arranged in a cosmic web of extraordinary beauty and intricacy. This web consists of dense filaments and walls, separated by vast voids. The filaments contain the highest concentrations of galaxies and dark matter. The voids, meanwhile, are nearly empty, containing only sparse, scattered galaxies. This cosmic web structure is a natural consequence of gravitational instability. The universe began nearly uniform, with only tiny density fluctuations. Over billions of years, gravity amplified these fluctuations. Regions that were slightly denser than average attracted more matter, grew denser still, and eventually collapsed to form the filaments and walls. Regions that were slightly underdense remained relatively empty, growing into the voids. The result is a structure of extraordinary complexity, with filaments stretching across hundreds of millions of light years, connected at nodes where particularly dense clusters of galaxies reside. This structure has been revealed through painstaking surveys of galaxy redshifts. Astronomers determine the distances to thousands or millions of galaxies by measuring the redshift of their light and converting that redshift to a distance using models of how the universe expands. By mapping the three-dimensional positions of galaxies, astronomers can visualize the cosmic web. Surveys, like the Sloan Digital Sky Survey, have revealed the large-scale structure of the universe in exquisite detail, showing the filaments and walls and voids in a way that would have been inconceivable a few decades ago. The scale of these structures is breathtaking. Individual filaments stretch across distances of 100 million light-years or more. Some of the largest structures, like the Hercules Corona Borealis Great Wall, span over 1 billion light-years. These are not gravitationally bound objects in the way that galaxies or clusters of galaxies are. You cannot hold one of these structures together with gravity alone. It would collapse under its own weight. Instead, these structures exist in a delicate balance between the gravitational attraction of the matter within them and the expansion of the universe itself. The question is, how long does it take for such structures to form? In the hierarchical picture, large structures form late. Small structures assemble first, merge into intermediate structures, which merge into larger structures, which eventually assemble into the largest structures. The very largest structures, the billion light-year filaments, should be the last to form, emerging gradually over billions of years, as gravity slowly amplifies the initial density fluctuations. But JWST observations suggest that coherent structures may have already been present in the early universe. While JWST is primarily sensitive to galaxies and the light they emit, the three-dimensional distribution of early galaxies revealed by JWST observations can give us clues about the underlying structure. What astronomers have found is evidence of overdense regions and underdense regions, the seeds of the cosmic web, already present when the universe was only a few 100 million years old. Some of this evidence comes from the observation of galaxy clusters in the early universe. Clusters are the densest knots in the cosmic web, where massive concentrations of galaxies reside. We have long known that clusters existed in the early universe, but JWST has revealed that they were more massive, more assembled, than hierarchical models expected. Other evidence comes from the distribution of galaxies, as seen in redshift surveys. Even though we do not yet have complete redshift surveys of very distant galaxies from JWST, we can infer the structure from the distribution of galaxies as they appear on the sky. If galaxies are clustered, if they prefer to exist near other galaxies rather than being randomly distributed, this is a signature of the underlying cosmic structure. Early surveys by JWST have shown that galaxies in the early universe appear to be clustered more strongly than expected. The implication is that the initial conditions of the universe may have been bumpier than standard inflationary models predict. Or perhaps the process of structure formation was more efficient, more rapid than conventional models suggest. Or perhaps there are aspects of physics that we do not yet understand that allowed structure to form more quickly in the early universe. It is worth pausing here to acknowledge the profound uncertainty that surrounds these interpretations. Astronomy is a science of observation, and observations, particularly of the distant universe, are subject to numerous sources of systematic error. The distance measurements rely on models of how light is absorbed and redshifted. The determination of galaxy mass relies on models of how stars are distributed within galaxies and how much dark matter they contain. The inference of structure relies on statistical analysis that assume certain properties of the universe. Each of these assumptions could, in principle, be wrong. When we observe a very distant galaxy and estimate its mass, we are making a series of assumptions about what kind of galaxy it is, how much of its light is obscured by dust, how much dark matter surrounds it. If those assumptions are incorrect, the estimated mass could be off by a factor of 2 or 3 or more. Multiply such uncertainties across hundreds of thousands of galaxies, and you can begin to see how the apparent discrepancy between observations and theory might, in the best case, reflect uncertainties in our measurements rather than a true inconsistency between theory and observation. Yet it would be equally wrong to dismiss the observations as merely uncertain. JWST has been designed specifically to reduce these sources of uncertainty. Its infrared sensitivity allows it to observe very distant galaxies that would be invisible to Hubble, and its spectroscopic capabilities allow for more precise distance measurements. The team that operates JWST is exquisitely aware of the sources of systematic error and has gone to great lengths to account for them. When they report the discovery of massive galaxies at high redshifts or overdense clusters in the early universe, they do so with careful attention to what assumptions have been made and what uncertainties remain. So we are left with a situation that is genuinely ambiguous. The observations could be telling us something profound about the nature of the early universe, about how quickly structure formed, or about some missing ingredient in our models of dark matter, gravity, or inflation. or the observations could reflect subtle biases in how we interpret the data, uncertainties that will be resolved as JWST continues to observe, and as complementary observations from other telescopes provide additional constraints. This ambiguity is not a failure of science. Science advances through the tension between observation and theory, through the careful examination of discrepancies, through the willingness to entertain multiple explanations until evidence points toward one. We are, in a very real sense, in the early stages of understanding what JWST has shown us. The observations are recent, the analyses are ongoing, and new data continue to arrive. Part 7. The light that came from nowhere. There is another aspect of the JWST observations that deserves careful consideration: the sheer abundance of faint galaxies in the early universe. When the deep field observations were first released, one of the striking features was not just the number of galaxies, but the distribution of their brightnesses. The observations showed far more faint galaxies than had been anticipated. This is significant because the number and brightness distribution of galaxies tells us something about the history of star formation. The total light output from all the stars in a galaxy depends on how much stellar mass the galaxy contains and what the ages of its stars are. A young galaxy, in which stars have only recently formed, will be brighter relative to its stellar mass than an old galaxy, because young stars are more luminous. As a galaxy ages, its stars age as well, and they become dimmer. Therefore, looking at the brightness distribution of galaxies at different distances, which is equivalent to looking at galaxies at different cosmic epochs, tells us how rapidly stars were being formed as a function of time. The standard picture of cosmic star formation is that the universe formed stars most rapidly during its first few billion years, when galaxies were actively colliding and merging, and when the supply of gas was most abundant. As the universe aged, the rate of star formation gradually declined. By the present day, the universe is forming stars at a much lower rate than it did in the past. This decline in the star formation rate is thought to be due to the cumulative effects of feedback: black holes blowing away gas, supernovae heating gas, the depletion of available gas through conversion into stars. But JWST observations suggest that there may have been even more star formation occurring in the very early universe than previously thought. The abundance of faint galaxies implies that there were more galaxies, or more stars per galaxy, or both, in the early universe than we had estimated. If this is correct, then the cosmic star formation history would be even more front-loaded toward the very early times than previously believed. What does this mean for our understanding of how the universe evolved? One implication is that there was more ionizing radiation in the early universe than we thought. Massive stars, stars born early in their lives, emit vast amounts of ultraviolet radiation. This UV radiation is energetic enough to ionize hydrogen atoms, knocking the electrons free from protons. In the very early universe, the intergalactic medium was filled with neutral hydrogen. As the first stars and galaxies formed, their ionizing radiation began to ionize this neutral hydrogen, transforming the universe from being opaque to radiation, at least at UV wavelengths, to being increasingly transparent. This process, called cosmic reionization, was thought to have occurred gradually over the first billion years or so of cosmic history, starting at redshift z equals 20 or so and continuing until redshift z equals 6 or so, by which time the universe was almost entirely ionized. But if there was more star formation in the very early universe than we thought, then reionization could have begun earlier and proceeded more rapidly. JWST has indeed revealed evidence that reionization proceeded more rapidly than previously thought. The universe appears to have become fully ionized by redshift z equals 5.5, or possibly earlier. This is consistent with there being more sources of ionizing radiation in the early universe than standard models predict. The presence of all these faint, early galaxies also has implications for the chemical composition of the universe. Stars forge heavy elements through nuclear fusion in their cores and scatter these elements across space when they die. The more stars that have formed, and the longer ago they formed, the more time has passed for subsequent generations of stars to incorporate these heavier elements. Observations of the chemical composition of distant galaxies and the intergalactic medium can therefore tell us about the history of star formation. The intergalactic medium shows evidence of heavy elements, oxygen, carbon, silicon, iron, already present when the universe was very young. JWST observations have confirmed that even galaxies at the highest redshifts observed, when the universe was only a few 100 million years old, contain evidence of heavy elements. This implies rapid star formation and rapid stellar evolution in the very early universe. The first stars must have formed quickly, lived short lives, and died, scattering heavy elements into their surroundings, and then new stars must have formed from this enriched material. All of this had to happen in the relatively short time span between the Big Bang and the epoch observed by JWST. The rapidity of these processes is breathtaking. In less than 300 million years, less time than it takes for the solar system to complete even a modest fraction of its orbit around the Milky Way, the universe went from being filled with only hydrogen and helium to containing vast numbers of stars, galaxies, black holes, and chemical enrichment from stellar alchemy. It is as if the universe was in a desperate hurry to build complexity, to generate diversity, to create the foundations upon which subsequent cosmic history would be built. Part 8. The Spectroscope and the Distant Truth. To understand how astronomers know what they claim to know about the early universe, we must consider the tools and techniques they employ. The primary tool is spectroscopy, the analysis of light broken into its component colors, or wavelengths. When light from a distant galaxy passes through a spectroscope, it is spread out into a spectrum, like a rainbow. Each chemical element, when heated, emits light at specific wavelengths. Hydrogen emits light at 656 nanometers, the red hydrogen alpha line, for 186 nanometers, the blue hydrogen beta line, and other specific wavelengths. Helium, oxygen, carbon, and every other element has its own characteristic emission lines. When astronomers observe a distant galaxy's spectrum, they can identify which elements are present based on the emission lines they see. But more than that, the positions of these lines contain crucial information about the galaxy's motion. If a galaxy is moving away from us, the light waves are stretched, and the emission lines are shifted toward longer wavelengths, redshifted. The amount of redshift is proportional to the galaxy's recession velocity, which is related to its distance via the expansion rate of the universe. This is how astronomers measure the distances to galaxies, by observing spectral lines and measuring how much they are redshifted. Hubble's original discovery that the universe is expanding was based on this technique. He observed that distant galaxies had redshifted spectral lines, indicating they were moving away from us, and that the farther away a galaxy was, the faster it was receding. For nearby galaxies, where spectroscopy is straightforward, this technique is reliable. But for very distant galaxies, the light is exceedingly faint. The photons from a distant galaxy have traveled for billions of years to reach Earth, and they are spread over a large area by the time they arrive at our telescopes. JWST is designed to collect as many of these faint photons as possible and analyze them. When JWST observes a very distant galaxy, it can measure its spectrum. The spectral lines are redshifted by the expansion of the universe, and by measuring the redshift, the distance to the galaxy can be calculated. But there is an important caveat. The relationship between redshift and distance depends on assumptions about the properties of the expanding universe. In particular, it depends on the values of the expansion rate at different times in the past, which in turn depends on the density of matter and energy in the universe. The currently accepted model is the Landau-CDM model, which includes ordinary matter, dark matter, and dark energy. The dark energy, represented by the cosmological constant, symbolized by the Greek letter lambda, is thought to accelerate the expansion of the universe. Using the Landau-CDM model and measured values of its parameters, astronomers can convert a measured redshift into a distance and an age for when the light was emitted. This process is straightforward in principle, but requires careful calibration in practice. The parameters of the Landau-CDM model are determined by fitting to observations of distant supernovae, the cosmic microwave background, and the large-scale structure of the universe. As these observations improve, the parameters are refined, and the derived distances and ages of distant galaxies may change slightly. But more than spectroscopy is needed to characterize a distant galaxy. Astronomers also use photometry, measuring the total brightness of a galaxy in different wavelength bands. By observing a galaxy in the infrared, visible, and ultraviolet, and measuring its brightness in each band, astronomers can estimate the galaxy's stellar mass, the age of its stars, the rate at which it is forming new stars, and other properties. The light from a distant galaxy is redshifted, so the visible light from the galaxy, emitted at wavelengths of a few hundred nanometers, is shifted into the infrared, where JWST is most sensitive. For a galaxy at Z=10, the visible light from the galaxy is shifted to wavelengths of a few micrometers, well into the infrared. JWST's infrared sensors are therefore ideally suited for observing such distant galaxies. But inferring the properties of a galaxy from its observed spectrum and colors is not straightforward. It requires fitting models to the observations. An astronomer might assume a particular star formation history, how rapidly the galaxy has been forming stars as a function of time, and then calculate what spectrum and colors the galaxy should have. By comparing the calculated spectrum to the observed spectrum, the astronomer can refine their assumptions and eventually arrive at a best fit model that describes the galaxy. This is where uncertainty creeps in. Different assumptions about star formation history, dust content, or stellar population can lead to different inferred masses and ages. Two astronomers analyzing the same galaxy might arrive at somewhat different conclusions if they make different assumptions. These differences are usually modest, perhaps a factor of 2 in estimated mass, or a few 100 million years in inferred age, but they are real. When JWST first released its deep field observations, some initial analysis suggested the presence of galaxies at redshifts that were extraordinarily high, Z=20 or higher, corresponding to a cosmic age of only a few tens of millions of years. These would be the earliest galaxies ever observed, formed in what would have been an impossibly short time after the Big Bang. However, subsequent analysis by multiple teams of astronomers suggested that some of these candidates were less certain than initially claimed. In some cases, the photometry, the brightness measurements in different bands, were consistent with multiple possible redshifts. A galaxy that appeared to be at Z=20 based on initial analyses might actually be at a lower redshift, Z=3 or Z=4, where formation is less problematic. The light might be reddened by dust, causing it to appear more distant than it actually is. This is the nature of scientific progress in astronomy. Initial discoveries are made, tentative claims are advanced, but then they are tested and scrutinized. Some claims are confirmed, others are refined or revised. The most robust results are those that have been independently verified by multiple teams using different methods. In the case of the JWST observations, the most robust conclusions are that there are many more galaxies in the early universe than previously thought, and some of them are more massive and more mature than expected. The exact numbers, how many galaxies, how massive, at what redshifts, remain somewhat uncertain and will likely be refined as more data accumulate. But the basic picture, that the early universe was more complex and structured than our models predicted, seems solid. Part 9. The universe older than itself. Before we continue, a philosophical interlude is warranted. We live in an age of unprecedented knowledge about the universe, yet this knowledge is purchased at the cost of a profound perplexity. We can measure the universe, map its structure, trace its history back to a fraction of a second after the Big Bang. And yet the very observations that reveal its nature also reveal the limits of our understanding. Consider the paradox that emerges from the JWST observations. We observe galaxies that appear to have been constructed with astonishing rapidity. We see black holes that seem to have grown impossibly quickly. We see structures that appear too large, too mature, to have had time to assemble. And yet, these are not speculative constructs. They are observed facts. Light that has traveled billions of light years to reach us. Photons that carry information from the ancient universe. In some sense, the early universe appears to be older than itself. The structures we see have characteristics that suggest they required more time to form than the cosmic age at which we observe them. This is a phrase worth unpacking. When we say the universe is a certain age, we are relying on a chain of reasoning that begins with our measurements of the expansion rate today, the density of matter and energy, and the properties of the cosmic microwave background. Using these measurements and the physics of general relativity and the Big Bang model, we calculate that the universe has been expanding for about 13.8 billion years. But what if our understanding of what happened in that expanding universe is incomplete? What if the process of cosmic structure formation was fundamentally different than our models suggest? What if the universe, in some sense, knows a shortcut, a way to build complexity more rapidly than linear gravity would allow? This is speculative territory, but it is worth exploring. One possibility is that cosmic structure formation was enhanced by processes we have not yet fully accounted for. For instance, feedback effects, the influence of supernovae, black hole accretion, and other energetic processes on the surrounding gas might operate differently in the early universe than in nearby galaxies. Perhaps in the dense, turbulent environment of the early universe, feedback was more effective at driving the assembly of structure, concentrating matter more rapidly than our simulations predict. Another possibility involves the nature of dark matter itself. We have assumed that dark matter is cold and collisionless, meaning it moves slowly, and does not interact with itself or with ordinary matter except through gravity. But if dark matter had some small amount of self-interaction, or if it could dissipate energy through some mechanism, then its dynamics could be different. It might clump more efficiently, allowing structures to form more rapidly. A third possibility involves modifications to gravity on large scales. General relativity, which is our best theory of gravity, has been tested extensively in the regime of strong gravity, near black holes, and weak gravity, in the solar system and beyond. But the behavior of gravity on the very largest scales, spanning tens of millions of light years, has not been tested as thoroughly. Perhaps general relativity is not the complete story, and some modification or extension of the theory is needed to explain cosmic structure formation in the early universe. A fourth possibility is that the universe had some special initial conditions that allowed rapid structure formation. Perhaps the Big Bang was not quite as symmetric as we thought, and the initial conditions contained significant structure on large scales. Or perhaps there were primordial black holes formed in the early universe that seeded structure formation. Or perhaps there were cosmic defects, topological relics from the very early universe, that acted as seeds for structure. Each of these possibilities has been explored by theorists and remains an active area of research. None of them has been ruled out by observations, and none of them has been confirmed as the correct explanation. We are in the situation of having a puzzle without a clear solution, but with several intriguing possible pieces. The deeper philosophical question is what this means for our understanding of reality. For centuries, science has advanced by breaking reality down into smaller and smaller pieces, by discovering simpler, more fundamental laws that govern the behavior of complex systems. We discovered that chemistry emerges from physics. We discovered that the properties of materials can be explained by the behavior of atoms and electrons. We discovered that the evolution of organisms can be explained by genetics and evolution. Cosmology represents an ultimate expression of this reductionist impulse. We attempt to explain the entire universe, all of its structure, complexity, and beauty, in terms of a handful of physical laws and initial conditions. The Big Bang model does this with remarkable economy. A universe of 13.8 billion years, governed by general relativity and quantum mechanics, containing ordinary matter, and dark energy, with initial conditions set by cosmic inflation, gives rise to everything we observe. And yet, the observations of JWST suggest that this economy might come at a cost. Perhaps the universe is not quite as simple as our models suggest. Perhaps there are missing pieces, additional mechanisms, or subtle complexities that our current theories have not captured. In seeking to understand the universe, we may need to think more deeply about what drives cosmic evolution, how gravity shapes structure, and what role the initial conditions played in determining the universe we observe today. Part 10. The Cosmic Horizon and What Lies Beyond. As we contemplate JWST's revelations, we are moved to ask, what is the ultimate fate of the universe? If it began with the Big Bang and has been expanding ever since, will it continue to expand forever? Will it eventually reach a maximum size and then contract back into a big crunch? Or will it find some equilibrium? For many decades, the answer to this question hinged on the amount of matter in the universe. If the universe contained enough matter, its gravity would eventually overcome the expansion, and the universe would begin to collapse. If it did not contain enough matter, expansion would continue forever, the universe would grow cold, and all structure would eventually dissipate. In 1998, observations of very distant supernovae revealed something unexpected. The expansion of the universe is not slowing down due to gravity. Instead, it is speeding up. The universe is accelerating. This was such a surprising result that it initially met with skepticism. But subsequent observations have confirmed it. The universe is being pushed apart by a mysterious form of energy called dark energy. The nature of dark energy remains one of the deepest mysteries in physics. It accounts for about 68% of all the energy in the universe, yet we do not know what it is. The simplest explanation is that dark energy is the cosmological constant, a property of spacetime itself, with constant density throughout space and time. This leads to a model in which the universe expands forever, exponentially, becoming emptier and colder with each passing eon. But dark energy might be something else, a dynamical field, evolving with time, with properties that change as the universe expands. Or it might be a sign that gravity itself, on the largest scales, behaves differently than general relativity predicts. Resolving the nature of dark energy is one of the great challenges facing contemporary physics. JWST's observations of the distant universe and the cosmic structure can potentially shed light on dark energy. The way structures form and cluster depends on the properties of dark energy, on how the universe expands at different epochs. By mapping the large-scale structure of the universe more precisely, measuring galaxy clustering with greater accuracy, and using other techniques, astronomers can constrain the properties of dark energy and perhaps eventually determine its nature. In the long term, the fate of the universe depends on dark energy. If dark energy is truly a cosmological constant with constant density, then the universe will continue to expand forever, eventually reaching a state of maximum entropy, in which all energy is dispersed, all stars have burned out, and only cold, diffuse radiation remains. This is sometimes called the heat death of the universe. Such an end seems infinitely distant. The universe is currently about 13.8 billion years old. The Sun will not become a red giant and engulf Earth for another 5 billion years or so. Civilization, as we know it, has existed for only a few thousand years. From the human perspective, the future evolution of the universe on timescales of trillions of years seems abstract, almost irrelevant. And yet there is something profound in contemplating it. All the structure, all the complexity, all the life and consciousness that will ever exist in the universe, assuming the current trajectory continues, will eventually be erased. The universe will return to a state of maximum disorder, maximum entropy, empty and cold and dark. It will be as if nothing ever happened. Or will it? Quantum mechanics suggests that even in a universe of maximum entropy, some kind of activity might continue at the smallest scales, processes occurring at rates so slow as to be virtually imperceptible. Hawking radiation might allow black holes to slowly evaporate. Protons might decay, eventually. The universe might be capable of surprising us even at times spanning incomprehensible durations. But for all practical purposes, if the universe continues to expand as currently predicted, its future is one of increasing darkness, increasing emptiness, increasing coldness. All the galaxies we observe with JWST, all the structures that took billions of years to assemble, will eventually disperse into the void. This thought might seem depressing, a kind of cosmic pessimism, but it carries within it a paradox. The fact that the universe will eventually die means that the present moment is precious. The existence of structure, of life, of consciousness, of beauty, these are not inevitable features of the universe. They are temporary, transient, contingent on particular conditions that have obtained for a brief moment in cosmic history. We are living in a golden age of the universe, a time when structure is abundant, when galaxies shine with the light of billions of stars, when at least one planet hosts life and consciousness capable of marveling at the cosmos. This age will not last forever. Eventually, it will end. But while it lasts, it is extraordinary. Part 11. The Mystery of Cosmic Abundance. Let us return to the observational mystery at the heart of our discussion. JWST has revealed 800,000 galaxies in a patch of sky no larger than a grain of sand held at arm's length. This abundance of galaxies has profound implications not just for the structure of the universe, but for what it means for the universe to be habitable, to contain conditions suitable for life. For decades, astronomers have speculated about the Drake equation, a famous formulation that attempts to estimate the number of intelligent civilizations in the Milky Way galaxy. The equation multiplies together various factors: the rate of star formation, the fraction of stars with planets, the fraction of planets suitable for life, the fraction of habitable planets where life actually arises, the fraction of life-bearing planets that develop intelligent civilizations, and the average lifetime of such civilizations. The Drake equation is useful as a framework for thinking about these questions, but it is hampered by the fact that most of its factors are deeply uncertain. We do not know what fraction of stars have planets, though recent surveys suggest the number is very high, perhaps nearly 100%. We do not know what fraction of planets are habitable. This depends on how we define habitability, what range of conditions life can tolerate. We do not know how frequently life arises, how often it develops intelligence, or how long civilizations last. But the implications of JWST's observations are worth considering in this context. The universe contains vastly more stars than we previously believed. There are not merely billions of galaxies. There are trillions, or perhaps even more. Each galaxy contains hundreds of billions of stars on average. The total number of stars in the observable universe is estimated to be around septillion, a number so large that it is effectively incomprehensible to human intuition. If even a tiny fraction of these stars host planets, and if even a tiny fraction of those planets are habitable, the total number of habitable worlds in the observable universe is staggering. Estimates suggest that there could be more habitable planets in the universe than there are stars in the Milky Way. In the face of such abundance, the question of whether life exists elsewhere becomes less a matter of speculation and more a matter of statistical inevitability. Given the vast number of possibilities, it seems almost more likely that life would exist somewhere than that it would not. This reasoning has been dubbed the mediocrity principle, the idea that humanity is not in any special location or condition, that we are average, typical, unremarkable in cosmic context. Applied to the question of life, it suggests that if life arose on Earth, it likely arose elsewhere as well. The sheer number of habitable worlds suggests that Earth is not unique in its capability to host life. And yet we must be cautious about this reasoning. The mediocrity principle is not a law of nature. It is a statistical statement based on assumptions about how life arises. We know of only one example of life on Earth. We do not know how easily life arises from non-living matter, how frequently it makes the jump from simple chemistry to self-replicating systems. It is possible that life is extraordinarily rare, that the conditions required for it to emerge are so stringent that even in a universe of trillions of habitable planets, life might exist on only a handful. There is also the Fermi paradox to consider. If the universe is full of habitable planets, and if life frequently arises on such planets, and if some life-bearing planets develop intelligent civilizations, then where are the aliens? Why have we not detected signals from other civilizations? Why have we not observed evidence of their activity or their presence? Various solutions to the Fermi paradox have been proposed. Perhaps intelligent civilizations are short-lived, rising and falling before they can spread across the galaxy. Perhaps they self-destruct, through war or accident, shortly after developing the technology that would allow them to become spacefaring. Perhaps they deliberately avoid contact with others, following some sort of prime directive, similar to that in science fiction. Perhaps they exist but are so far away that their signals have not reached us, or are in forms we do not recognize. Or perhaps, despite the abundance of habitable worlds revealed by JWST, intelligent life is rarer than the mediocrity principle would suggest. Perhaps the road from chemistry to biology to intelligence involves hurdles that are higher than we imagine, requiring rare combinations of circumstances. Perhaps we are, after all, in some sense exceptional, not in our location or our basic physical composition, but in having made the transition from mindless matter to conscious, reflective beings capable of wondering about the cosmos. These are not scientific questions that can be answered with observations and equations. They are questions that touch on the nature of consciousness, the role of chance and necessity in the universe, the meaning of existence. They are the kinds of questions that have occupied philosophers and theologians for millennia, and that will likely occupy us for millennia more. But JWST's revelations provide a new context for these ancient questions. We now know that the universe is even vaster, more abundant, more filled with possibility than we previously imagined. If we are alone, our solitude is more profound and more poignant. If we are not alone, then there are trillions of potential worlds out there, each with its own history, its own story, its own inhabitants struggling with their own existential questions. Part 12. The Physics Yet to Come. To move forward in understanding what JWST has revealed, we must look ahead to the physics that still needs to be developed or refined. The current state of cosmology is one in which the major features of the universe are understood: the Big Bang, cosmic expansion, the formation of the cosmic microwave background, the growth of large-scale structure, but the details remain fuzzy. We know how the universe evolved in broad strokes, but the mechanics of that evolution, particularly in the very early universe and on the largest scales, remain incompletely understood. One avenue for progress is through improved observations. JWST is operating now, and will continue to operate for years to come. Its primary mirror has a surface area of 25 square meters, about 6 times larger than Hubble's. This larger collecting area means it gathers more light and can detect fainter objects and smaller details. As JWST continues its observations, accumulating more data on distant galaxies, the census of early galaxies will become more complete, the measurements will become more precise, and some of the current ambiguities will be resolved. But there are also other observational approaches on the horizon. The next generation of ground-based telescopes, the Extremely Large Telescope, the Giant Magellan Telescope, the 30-meter telescope, will be equipped with adaptive optics systems that can correct for the distorting effects of Earth's atmosphere, allowing them to achieve angular resolution comparable to or better than space-based telescopes. These telescopes will be able to obtain detailed spectroscopy of distant galaxies, providing precise measurements of their properties. Meanwhile, radio observations continue to improve. The latest generation of radio interferometers, such as the Very Large Array and the Atacama Large Millimeter/Submillimeter Array, can detect some of the most distant galaxies through the radio emission they produce. Radio waves, unlike visible light, are not as strongly absorbed by dust, so they can penetrate through regions of the universe opaque to visible light. Future radio telescopes, such as the Square Kilometer Array, will provide unprecedented sensitivity to the radio universe. From the theoretical side, progress is being made in understanding the physics of the early universe. Simulations of cosmic structure formation have become increasingly sophisticated. Modern simulations can follow the evolution of dark matter, ordinary matter, stars, and black holes in a volume of the universe comparable to what JWST observes. These simulations implement the known physics of gravitation, hydrodynamics, and stellar and black hole feedback, and they show how structure emerges from initial conditions. Comparing these simulations to observations provides a way to test theories. If the simulations produce galaxies that match what JWST observes, then our understanding is sound. If the simulations produce galaxies that differ from observations, then we need to refine our understanding of one or more of the physics processes involved. Currently, simulations tend to produce fewer massive galaxies in the early universe than JWST observes, and black holes that are less massive. This suggests that either the feedback from supernovae and black holes is weaker than models assume, or the initial conditions of the universe contain more large-scale structure than simulations typically implement, or some other physical process is at play. One intriguing possibility involves the role of magnetic fields. In the early universe, magnetic fields could have played a larger role than they do in the present-day universe. Magnetic fields can affect the dynamics of gas, supporting it against collapse in some directions while allowing it to collapse in others, creating filamentary structures. Magnetic fields can also amplify turbulence, enhancing mixing and allowing structure to form more efficiently. In recent years, simulations that include detailed treatment of magnetic fields have shown promise in reproducing some of the features of the early universe observed by JWST. Another possibility involves the role of primordial gravitational waves. These are ripples in the fabric of space-time itself, produced by the most violent events in the early universe. Cosmic inflation is believed to produce a background of primordial gravitational waves, and if these waves had sufficient amplitude, they could drive the formation of structures on certain scales. Future observations, particularly by gravitational wave detectors, could reveal whether primordial gravitational waves played a significant role in cosmic structure formation. The ultimate goal of such theoretical work is to arrive at a complete understanding of how the universe evolved from the Big Bang to the present day, an understanding grounded in physics and consistent with all observations. We are not there yet. There remain gaps in our knowledge, puzzles that do not fit neatly into current frameworks, mysteries that call for deeper insight. But this is the state that science works best, at the frontier between known and unknown, where observations challenge theories and theories guide the search for new observations. We are in such a state now, thanks to JWST's remarkable capabilities. The puzzle pieces are being turned over, examined, and slowly assembled into a picture that is becoming clearer, even as new details emerge to perplex us. Part 13. The Moral Dimension of Cosmic Scale. As we near the end of our meditation on JWST's revelations, it is worth considering what these discoveries mean not just scientifically but morally, philosophically, existentially. We live in a time of great human conflict, inequality, and suffering. Wars rage, poverty persists, injustice is rife. In the face of such challenges, one might ask, what does it matter that the universe is larger than we thought? How does the discovery of 800,000 galaxies in a patch of empty sky speak to the human condition? The answer is subtle. These discoveries do not directly address human suffering or injustice. They do not feed the hungry, cure disease, or resolve conflict. But they do something perhaps even more profound. They change our perspective on ourselves and our place in the cosmos. For most of human history, the universe was thought to be centered on Earth. We were the pivot point around which all heavens revolved. This was not merely a scientific error. It was profoundly indicative of how humanity viewed itself, as central to creation, as the reason the universe existed. The Copernican revolution displaced Earth from the center, but it took centuries for this realization to sink into human consciousness. Even today, in some sense, humanity has not fully internalized what it means to be on a planet that is not the center of anything. The revelations of modern astronomy, culminating in the observations of JWST, carry forward this theme. We live on a planet that orbits a modest star in a galaxy containing hundreds of billions of stars. Our galaxy is one of trillions. Our universe is so large that comprehending its vastness requires inventing new linguistic constructions, new metaphors, new ways of thinking. In the face of such perspective, human conflicts seem small, petty, almost laughably insignificant. And yet they matter. They matter to the humans involved. They matter to the families torn apart by war, to the children denied education and opportunity by poverty, to the individuals suffering injustice. The fact that our suffering is cosmically insignificant does not make it any less real or any less worthy of our attention and action. What JWST's observations offer is perhaps a kind of cosmic humility. They remind us that we are not the measure of all things, that the universe does not revolve around human concerns or human drama. This recognition can be liberating. If we are not the center of creation, then we are free to define our own meaning and purpose. We are free to focus on what matters to us: love, knowledge, compassion, beauty, justice, not because the universe demands it, but because we choose to value these things. There is also an implicit environmental message in JWST's observations. We live on a pale blue dot, a planet teeming with life, orbiting an ordinary star in a vast cosmos. This planet, with all its beauty, all its biodiversity, all its human culture and history, is the only home we have. There is no backup planet, no second Earth awaiting us. Whatever we do to our world, we will have to live with the consequences. The recognition of our cosmic insignificance combined with the uniqueness of our planet should instill in us a sense of stewardship, a responsibility to preserve and protect this remarkable world. JWST's observations also have implications for how we think about human knowledge and achievement. Here is an instrument, built by thousands of engineers and scientists from multiple nations, launched into space, positioned at the Earth-Sun L2 point, and operated with such precision that it can detect photons from galaxies billions of light years away. The fact that we can do this, that we have developed the technology, the mathematics, the scientific understanding necessary to probe the universe to such depths, is a remarkable testament to human achievement. And yet this achievement comes at a cost. The pursuit of scientific knowledge requires resources, institutional support, years of training and education. Not all humans have access to such opportunities. There is a privilege associated with being part of the scientific enterprise, a privilege that is not equally distributed across humanity or across nations. As we celebrate JWST's achievements, we should perhaps also reflect on what it would mean to extend similar opportunities for knowledge and discovery to all people. Part 14. The Mirror in the Sky. JWST is, in a very real sense, a mirror. It reflects our questions back to us. We built it to look outward, to observe the universe. But the questions we ask of it, the way we interpret its observations, the frameworks we use to make sense of its data, all of these reflect who we are, what we value, what we are curious about. The early observations of JWST revealed a universe more populous than we expected. We immediately asked, how did these galaxies form so quickly? How did these black holes grow so massive? These questions reflect our assumption that the universe should operate according to certain principles, that there are limits to how rapidly structures can form, that there are rules to how physics works. But perhaps this reflects a particular perspective, a particular way of thinking about causality and time that is rooted in human experience. In our everyday lives, we experience time as flowing in one direction, from past to future. We experience causality as a chain of events, each caused by preceding events. We experience growth as gradual, as requiring time. The universe, in its early moments, operated according to different rules. Physics itself was different. The fundamental forces were unified. Particles had different masses than they do today. The density and temperature were so high that quantum gravity effects dominated. The universe did not obey the same rules that govern the nearby universe we are familiar with. Yet we are trying to understand the early universe using concepts and frameworks developed to understand the nearby, present-day universe. We think in terms of galaxies that grow through mergers, of black holes that grow through accretion, of structures that form through the slow accretion of gravity. But perhaps in the early universe, the processes were different. Perhaps growth happened in ways we have not imagined, through mechanisms we have not accounted for. This is speculative, but it points to a deeper truth. Our understanding of the universe is always filtered through our perspective, our concepts, our way of thinking. We can never observe the universe from the outside. We are always inside it, trying to make sense of it from our particular vantage point. JWST helps us see farther, measure more precisely, detect fainter objects. But it cannot escape this fundamental limitation. We are always interpreting the universe through the lens of human understanding. This does not mean that our understanding is merely subjective or arbitrary. Science has methods to constrain interpretation, to distinguish between what is supported by evidence and what is not. But it does mean that there is an irreducible element of human perspective in all scientific knowledge. JWST, looking back toward the beginning of time, is also, in a sense, looking into a mirror. It is showing us the universe as it was, yes, but also how we think about the universe as it is, how we ask questions of nature, how we construct theories, and test them against observations. The 800,000 galaxies in a patch of empty sky are real, but they are also a reflection of our current state of knowledge, a snapshot of what we know and do not know at this moment in history. Part 15. The Horizon of Understanding. As we contemplate JWST's revelations, we are moved to ask, what is the ultimate fate of cosmological understanding? Will we ever fully explain the universe? Will there always be mysteries at the frontier of knowledge? The history of science suggests that as we solve one problem, new problems emerge. Newton's laws seem to explain the motion of celestial bodies with precision, yet Einstein showed that they were approximations of a deeper theory. Thermodynamics revealed the second law, that entropy always increases, and it took decades to understand the microscopic basis of this law in terms of the statistics of atoms and molecules. Quantum mechanics resolved mysteries about atomic structure and radioactivity, yet it opened new questions about the nature of reality and the role of observation in determining what we measure. There is no reason to think that cosmology will be different. We may eventually arrive at a complete understanding of how the universe evolved from the Big Bang to the present day. We may develop a theory that unifies general relativity and quantum mechanics, resolving the singularities and infinities that plague our current models. We may even understand the very first moment of the Big Bang, the moment of creation itself. And yet, at that point, new questions would inevitably arise. Why is there a universe at all? Why do the fundamental constants of nature have the values they do? Is our universe the only one, or are there others? These are questions that may ultimately transcend science, that may belong to the realm of philosophy or even theology. Science is, in a fundamental sense, a conversation between human curiosity and the universe itself. We ask questions, we make observations, we construct theories, we test them. The universe provides answers, but these answers often raise new questions. This process has been going on for centuries, and will likely continue for centuries more. JWST represents a milestone in this ongoing conversation. It is a tool of unprecedented power and precision, capable of seeing farther into space and deeper into time than any previous instrument. The revelations it has provided, the 800,000 galaxies, the impossibly massive black holes, the structures assembled too quickly, have opened new chapters in the story of cosmic origins. But they have also posed new challenges, new mysteries, new questions that demand answers. In this sense, JWST's greatest achievement may not be the specific discoveries it has made, but rather the questions it has provoked. By revealing the universe to be more complex, more mysterious, More filled with surprises than we thought, JWST has renewed the call for deeper investigation, for bolder theorizing, for the kind of creative thinking that has always driven science forward. Part 16. The Gift and the Mystery. The James Webb Space Telescope is humanity's gift to itself and to the universe. It is a gift wrought from human ingenuity, human creativity, human patience and perseverance. Thousands of people devoted years, some devoted entire careers, to designing it, building it, testing it, launching it, and operating it. They worked in collaboration across national boundaries, across language barriers, united in the desire to understand the cosmos. JWST is also a gift from the universe. The fact that the universe is transparent enough that we can see across billions of light years, that light from distant galaxies can reach us with enough intensity to be detected, that the laws of physics are mathematical enough that we can formulate theories to explain observations. All of these are remarkable facts that are not, in any fundamental sense, necessary. The universe could have been opaque to light. The light from distant galaxies could have been absorbed or scattered so severely that nothing could be seen beyond the nearby universe. The laws of physics could have been so complex, so chaotic, that no predictive theory could ever be formulated. Mathematics could have been inadequate to describe nature. Consciousness could have been impossible, and there would have been no observers to wonder why there is something rather than nothing. Yet here we are, conscious observers in a transparent universe governed by mathematical laws, able to build instruments of remarkable sensitivity and precision, able to detect photons that have traveled for billions of years, able to piece together the history of the cosmos from the light we collect. We are the universe becoming aware of itself, in the poetic formulation of Carl Sagan. We are stardust asking questions about our origins. JWST's revelations remind us of how much we still do not understand. The 800,000 galaxies in a patch of empty sky, the massive black holes in the early universe, the structures that seem to have formed too quickly, these are not just puzzles to be solved. They are invitations to think more deeply, to question our assumptions, to imagine how the universe might be different from what we believe. There is a temptation, in the face of mysteries, to throw up one's hands in despair, to declare that we can never understand the universe, that our knowledge is forever limited. But this would be a premature surrender. Science has overcome seemingly insurmountable mysteries before. Phenomena that were inexplicable have been explained. Paradoxes have been resolved. New frameworks have been developed that encompassed and transcended old understanding. The history of science is one of progressive enlightenment, punctuated by periods of confusion and frustration, but generally trending toward greater understanding. We understand more about the universe today than we did 100 years ago, and far more than we understood 1,000 years ago. JWST's observations are part of this grand progression, moving the frontier of knowledge outward, revealing new mysteries that invite future investigation. Part 17. The Measure of Wonder. In the end, perhaps the greatest gift that JWST offers is not a specific measurement or discovery, but a renewal of wonder. Wonder is the birthplace of science, the fundamental emotion that motivates humans to ask questions, to seek understanding, to venture into the unknown. We are creatures driven by curiosity, by the desire to understand ourselves and our world. JWST shows us a universe that is vaster, more complex, more abundant than we had imagined. It shows us that the cosmos contains mysteries that challenge our understanding, that the universe is not a closed book but an open one, with many chapters yet to be written. It shows us that there is still so much to learn, so much to discover, so much to wonder about. The 800,000 galaxies in a patch of empty sky are more than data points in a cosmic census. They are witnesses to the history of the universe. Each one is a system unto itself, containing billions of stars, potentially trillions of planets. Each galaxy has a story, how it formed, how it evolved, what role it played in the assembly of cosmic structure. Some of these galaxies may harbor life, may host conscious beings who look up at their own night skies and wonder about the cosmos, just as we do. We do not know what lies in those distant galaxies. We do not know what forms life might take in that distant universe, what physics might operate under different conditions, what civilizations might have arisen and fallen in the incomprehensible spans of cosmic time. We can only imagine, and in that imagination lies another form of wonder, the wonder of possibilities, of potential, of paths not yet taken. JWST reminds us that science is not a finished enterprise, not a body of knowledge that has solved all the mysteries and explained all the phenomena. Rather, science is an ongoing process of discovery, a conversation between observers and the universe, a dialogue in which each answer reveals new questions. The universe remains, in many ways, as mysterious as it was before JWST. But it is a more interesting mystery now, richer in detail, more complex in texture, more fertile with implications. The true scale of the universe, revealed by JWST, is measured not just in light years and galaxies and cosmic age, but in the depths of mystery that remain. It is measured in the questions we still cannot answer, in the phenomena we still do not fully understand, in the future discoveries that await us. As long as there are mysteries, there is wonder. And as long as there is wonder, there is motivation for science, for exploration, for the eternal human quest to understand ourselves and our place in the cosmos. Coda, the unfolding. We stand at a moment of transition. JWST is only beginning its work, having been operational for less than 4 years at the time of this writing in early 2026. The deepest observations, the most precise measurements, the most revolutionary discoveries may still lie ahead. Each observation JWST makes adds a thread to the tapestry of our understanding. Each new data point constrains our theories, guides our thinking, opens new avenues for investigation. We have become accustomed to revising our understanding of the universe on the basis of new observations. The expansion of the universe was discovered by Hubble in 1929. The cosmic microwave background was discovered accidentally in 1964. The acceleration of cosmic expansion was discovered in 1998. Major revisions of our cosmological models have occurred on the timescale of decades or less. It is reasonable to expect that further revisions will come as JWST and other instruments gather new data. What will future astronomers make of our current state of knowledge, our current puzzles and mysteries? Perhaps they will look back at the early observations of JWST with the knowledge that the mysteries have been solved, that the apparent impossibilities have been explained, that what seemed incoherent has been integrated into a larger framework of understanding. Or perhaps they will find that the puzzle was deeper than we imagined, that the solution required a more fundamental revision of our ideas about physics, about gravity, about the nature of space and time itself. In any case, the universe will continue to reveal itself, to open its secrets to those patient and clever enough to ask the right questions, to make the right observations, to think through the implications. JWST is merely one instrument, albeit a remarkable one, in humanity's ongoing effort to understand the cosmos. It is a milestone on an infinite journey, a stepping stone in a path that leads ever deeper into the heart of reality. The true scale of the universe is not measured in kilometers or light years, vast though these distances are. It is measured in the scope of questions we can ask, the depth of mysteries we can explore, the heights of understanding we can achieve. As JWST gathers light from the ancient universe and transforms it into images and spectra, it reveals not just the universe as it was, but the universe as it is, vast, complex, beautiful, and filled with wonders that continue to inspire awe and curiosity in those who pause to contemplate them. In the light of distant galaxies, collected by a telescope orbiting far from Earth, we find mirrors reflecting not just the cosmos, but ourselves, conscious beings, capable of wonder, reaching out across the void to understand the universe from which we emerged. This is perhaps the deepest scale of the universe, not the vast distances and immense durations, but the profound connection between observer and observed, between consciousness and cosmos, between ourselves and the light from the ancient universe that carries within it the story of creation itself. A final reflection on the nature of our knowledge. To write this extended meditation on JWST's revelations is to participate in an ancient human tradition, the attempt to make sense of the cosmos, to translate observations and data into meaning, to place our species and our existence within the larger context of the universe. Carl Sagan, whose voice echoes through these pages, once said that science is not just a collection of laws and facts, but a way of thinking that emphasizes evidence, respects uncertainty, and recognizes that human knowledge is fallible and corrigible. JWST's observations embody this spirit. They reveal the universe to be more complex than we expected, more abundant, more mysterious. They show us that our understanding is incomplete, that there are questions we have not yet learned how to ask properly, that there are phenomena that do not fit neatly into our current frameworks. And in revealing these gaps, JWST invites us to think more deeply, to develop new theories, to venture further into the unknown. The universe is not a fixed thing, complete and finished, waiting only to be catalogued. It is a process, unfolding, evolving, revealing itself through time. We are part of that process. Our observations, our theories, our attempts to understand are themselves part of how the universe becomes conscious of itself, part of the cosmic story. JWST, peering back toward the beginning of time, is helping to write that story, to illuminate the first chapters, to set the stage for future discoveries that we cannot yet imagine. The true scale of the universe, ultimately, is the scale of wonder itself, endless, infinite, inexhaustible. And as long as we maintain that sense of wonder, as long as we continue to ask questions and seek understanding, the universe will continue to reveal its secrets, one photon at a time, one discovery at a time, one moment of insight at a time. The journey continues, and the horizon of understanding forever beckons us forward into the mysteries that define the cosmos and, by extension, ourselves.